modern real clocks. Then impact of unbalanced skew on setup timing. Then, then the second one is that. And third one is impact of unbalanced skew on hold timings. Oh, so we have covered up basic violations of our setup time and hold times with the skews, that which is one of the major part of real clocks and performance degradation in the ongoing circuit. See, static timing analysis eliminates the need for comprehensive stimulus and provides exhaustive analysis of timing path by computing the timing arcs between all inputs to output paths in the design. So there are many different paths from input to outputs. What static timing analysis there did there, it actually make the circuit of different parts, and then it took the analysis of propagation of clocks with respect to, and as well as and with respect to this clock, what are the circuit excitation, that means datas flow on that path. See, static timing analysis is considered an efficient method for performing case analysis that ensure all critical paths meet their timing requirement for a given design. Owing to the efficiency of static timing analysis, it is used as a core engine in many layout synthesis tools, allowing one to analyze timing requirement as more information become available during different stages of physical design. It's one of the fantastic tool to not only lay down the better performance of a circuit, as well as a robust design we will get from the static timing analysis. See, in principle, static timing analysis uses arrival time, and in a similar fashion, static timing analysis uses required time. The relation between hold in order for the circuit to function properly is that the arrival time (TR) should be greater than the required time (TR) should be greater than TA, arrival time. Always, to work for a better to work a circuit properly, this is one of the requirement. Static time analysis tools make use of timing graphs to compute the values of TA and TR. The timing graph is created automatically. There is a directed graph. Each port is represented by a node. Nets connecting these ports by an edges. The start, the ending points of interconnection determined by the net list. Internal edges of each cell determine their timing arc. Define the library. We will have a diagrammatic view also, but before that we must understand the philosophy behind there. What is the actual technique they use over here? At each node, we are coming over, have an associated with positive or negative time slang. That means how much time it will differ in between arrival time and required time. So if this formula is this is TR is greater than TA, then it is a positive, or then it is, if it is less than, then it is less than 0, that means a negative. Total number of timing slack needed is proportional to the number of sequential elements that are used and have a tendency to grow exponentially as the design size increases. See, timing graph representations here. These are direction for required time calculation and direction for arrival time calculations. See, this much of kind of data are here, different kind of elements over there. So they will give us the these output points and input points become the nodes, and this is the path for, this is one path, this is the second path, this is the third path, they become the path. And what we have designed here, so they will become graph, a node net connecting these put by edges. They will be edges. We will go ahead. In order to improve efficiency and accuracy of static time analysis, one must include in the circuit a true path or a false path. What is true path? A true or false path is defined as a set of connected gates that start from one input and end at another input. True path is a path which actually fabricate the timing analysis of timing of the different devices, these buffers, flip-flops, etc. And first path is the path in which you assume that this is a path, but it actually won't exist there. for creating all the false paths. An iterative approach is applied during physical design to identify all possible false paths. How much we can divide there? Like this, it will go from this. Determine path false path is automatically. This is done in STA. Automatic false path generation in STA. Process of sensitization. A gate is considered to be sensitized if a signal transition can propagate through it from a particular input to the output, as long as the other input has non-controlling values such as logic value of 1 at input of NAND gate or logic value of 0 at input of OR gate. This is provide the controlling logic value. This must be there. If this is the a non-controlling value side input, so this is side input path, then side input and path station. This is, but this is sensitization criteria. This is side input and path criteria. It is for AND gate. It is for AND gate. Consider from this, it is a false path, automatic false path generation. One of the AND gate or value 0 at input or OR gate. Sensitization criteria. Sensitization specific conditions are referred to as sensitization criteria, and they can be statically or dynamically. We will go for static way numerically, and then we will provide them dynamically also. See, for a sensitizing criteria to be static, there must be a set of input vector that create non-controlling static to all side inputs along a path. Non-controlling logic 1, logic 0, this is non-sensitized path, and this is a sensitizer path, because it must exist set of input vectors that create non-controlling which are static to all side inputs along a path. This is all static paths, both of them. So this is non-synthesized path. The objective of dynamic sensitization criteria is to generate a set of input vectors such that when they are applied at different times, they have to apply at different times. They will produce non-controlling logic values, non-control at side inputs when the propagating transition signal at a particular gate. See, this is a side input at logic 0 1 at the time t1, and this is logic 1 to 0 at time t2. So what they are dynamic at 0 time t1, they have logic 0 and the side input logic 1 at time t2. So the objective is to generate a set of inputs such that when they are applied to at different times, that they will produce non-controlling logic value at side input in the particular gate. From a timing analysis point of view, several timing paths are a matter of interest. These types of timing paths are input to registers, register to registers, register to registers, register to output, and input to output. Both whole is input to output. Most timing analysis of an ASIC is a function of process, voltage, and temperature. This is PVT, process voltage, and is based on the assumption that the entire device is impacted by a single PVT condition, that is worst case. It is sometimes potential voltage and temperature also. The impact of these types of variation on chip timing cannot be analyzed by standard timing clocks using single PVT condition, such as worst case timing scenario for setup checks or best case timing scenario for hold checks. Why we need setup worst case timing for scenario for setup check? Because setup checks and hold checks are opposite to each other. In performing OCV analysis, that means on-chip variation analysis, one must compare computed pair of timing or delay here. For setup check, the worst PVT condition is used for clock and data path, launch path, clock and data path for launch path, and the best PVT condition is used for reference clock for capture path. Now, static timing analysis with real clock. Second, we will discuss on impact of unbalanced skew on setup timing. Signal propagation delay in logic gates was the main contributor to signal delay. I'm going through the theory, which is why this somehow. Uh, while wire delay was negligible, technology scaling significantly increased the relative impact of wiring induced delays, making high quality placement and routing critical for time. So what we need timing optimization right now because of the complexity of circuit. Engine must estimate circuit delays quickly and accurately to improve circuit timing. Timing optimizers adjust propagation delays through circuits components with the primary goal of satisfying timing constraint, including setup that they will be long path constraint, which specify the amount of time and data input signal should be stable or steady before the clock age for each storage element, for example flip-flop or latch. That means data should be stable, should be present when the clock age, when the clock should come over there. If it is positive trigger, then positive age should be there. For positive age, data should be present there, should be stable data should be present, and if negative age trigger, then the data should be present for negative trigger. Setup constraint ensure that no signal transition occurs too late. Initial phase of timing closer focus on these type of constraints, which are formulated as T cycle of that is clock cycle must be equal to combination delay, setup and skew. In ST, a combination logic network is represented as a directed acyclic graph. DAG. DAG is a directed acyclic graph where 0, 0, 0.6, these are the their 0, 0, 0.6. They have the input at which time they will be present input over there. At point 1.5 shows the delay. This 0 should be reached to the 0. This 0.6 time, that means it start from 0.6 and the delay will be there. The propagation delay, delay is 0.1. So this is how a DAG is created for a combination logic network where these are the y2, that means this is much of delay occurs by this much of delay, or this is the delay because of this. DAG representation using gate node conversion circuits. Right now, every gate in which this circuit, in this circuit, has been represented by a node A0, B0, C0, X1, Y2, these are you see X1, Y1, Z1, W1, these are they have been represented by nodes. And inputs of the circuits A0, they will start from this. This is the starting of this. So they will to reach from this to 0.06. So this is how, and the delays will be. So this is how a directed acyclic graph DAG has been constructed from this combination logic network. And then actual arrival times of the DAG denoted by A. See, this is A0, A0, A.6. It reach over here at 0.6 time. From there it will look from arrival times. So we are measuring arrival times here. Then what we, the required arrival time, the DAG denoted by R is this. This is 0.95. This is minus 0.35. This is 0.95. So actual arrival time is this much. Required arrival time. Actually this is required. Then the ST result showing the actual required arrival time and the slack of it, that means how much they will differ. There is a delay in them. This is 0.95. This is 0.35. Slack is this. So we have a broad idea of all the slacks associated with the paths. The slack of a node B defined as slack of required arrival time minus actual arrival time is an indicator of whether the timing constraint for V has been satisfied. Critical paths or critical lines are signals that have negative slacks, while non-critical paths or non-critical lines have positive slacks. See, this having a negative slack, so this path is a critical path. and both of them, because they have positive slack, because they have positive slack, they are non-critical paths. That's having positive. Timing optimization, now we have again covered, is the process by which negative slack is increased to achieve design correctness and positive slack is reduced to minimize over design and recover power area. See, negative slack has been put the deficiency in our circuit performance, because there is a mismatch, you see, mismatching of clock and delay, clock and datas. But and positive slack is reducing, give us the power to minimize the power and area and to recover them. There are two aspects to the optimization. One is timing budgeting and second is timing correction. First is timing budgeting. Target delays are allocated to hours along timing paths to promote timing closure during the placement and routing is. See, all the hours have been denoted by budgets. See, we will discuss this again. Budgets. That this much of timing closer, this has to be completed in this much of time. That is budget also. Then timing correction, the netlist is modified to meet timing constraint using such operation as changing the size of gate, inserting buffers and netlink restructuring. This is what happened during our placement when we find this or correction, sorry, clock resynthesis operation, where we find the actual budgeting is not meeting there. So we will do inserting buffers, size of gate and netlist casting. In practice, a critical path of minimum slack nodes between two sequential elements is identified and timing optimization are applied to improve slack without changing the logical function. That is here. See, this is a critical path. We will optimize both of them according to this by using some constraint here. So gate sizing, how it reflects as gate delay versus load capacity for 3 gates in increasing order. See, delay is this, and these are the load capacitors. That means the size of that. A, B, C. For we have shown this. These are A. This is for A. This is for B. This is for C. For 0.5 load capacitance, the delay is 15, 18, 23. As you go on increasing the load capacitances, you will find the delay is also increasing. So sizing is important. If we need a low delay, then we need a low gate. Sorry, low gate. See this one. Size, gate size. Resizing gate B from gate size A to size AC can achieve a lower gate delay. See here, A, B, D, E, F is a circuit. What we did here, we will do A, B, V, A, where the this 40 delay is 40. So D, E, F, CD is 1.5, 10. How will we change them? We got this. We have changed VA by VC, and at that time it is 28 and load should be 1.5, 10 and 0.5. By merely changing the gate, we have improved the performance of our circuit by resizing that. Then buffering, you see there A, B, V, B. What we did here, we have provided a buffer over here. So D, 1, so we got this. Improving by VB, the timing of inserting buffer wire to partially shield VB is to load capacitance. This much of load capacitance that will be shielded from it. Right now, it is actually looking after that. VB is not seeing it. So partially it is shielded by this. This is one of the buffering cells. Then netless recursive. We do what is netless recursive? We do cloning, replication of the. This is VB. What we do the VA, VB we will put over here, and we will manage them this way. Cloning or duplicating gates to reduce maximum local fanouts. This is VB, which is VA is a duplicate of VB there, and this is how we achieve the timing delay reduction. Cloning transformation. A driving gate is duplicated to reduce remoteness of its fan out. This is transformation. Redesign of fan entries. See, this is how we redesign them, and we get all of them off. Redesigning a fan entry to have a smaller input to output delay. The arrival times are denoted in angular brackets. These are the arrival times, and the delay are denoted in parentheses. These are the delays to them. Redesign of fan out tree. This is path this. They will again path 2. It will be look better than this. We put this in this. Redesign fan out tree to produce the load capacitor to reduce the load capacitance of path 1. It will be good to reduce here. Swapping commutative pins. Here, swapping commutative pins. Which pins are commutating? We will find out them and then we swap them here. A2, B1, and this is Y3. Find out. This is 5. This is 3. What we are doing here? We are swapping the pins. How? What we did there? C2 is come to this place. B is which actually change the position of A and B, and this is how we reduce the arrival time at F. See, this is without swapping of this. Go to and calculate. Gate decompositions. How? This is the actual circuit. We find out this circuit. We will make a different circuit and we will decompose in different gate decomposition complex network into an alternated network. Then Boolean restructure. This is a Boolean structure which having their arrival time syntax. We will again restructure this using logic property. For example, distributed law. These are the laws we are familiar with the Moore's law in your digital design to improve timing. And this is how we improve the timing using Boolean restructure. What is the reverse transformation? The timing reverse transformation is again as buffering, sizing, cloning increase the original area of the design. This is what the problem occur. That means we need a large die area. This change can cause the design to be illegal as some new cells can now overlap with other. To maintain legality, we either perform the respective reverse operation by person, that means downsizing and merging, or perform placement legalization after all timing corrections. Two things we do there: downsizing and merging, or legalization of all the timing corrections. So this is how we do unbalanced skew of setup time. Right now we go for impact of unbalanced skew on hold timing and how we cure this. Let me go through. Hold time, that is known as short time constraint, is specify the amount of what is the hold time. It specify the amount of time and data input signal should be stable after the clock age at each storage element. During setup time, I am going to hold time constraint ensure the signal transition do not occur too early. Hold violations cannot occur when a signal path is too short, allowing a receiving flip-flop to capture the signal at the current cycle instead of next cycle. The hold time constraint is formulated as either T com delay must be greater than or equal to T hold or T skew. As clock skew affects hold time constraint significantly more than setup constraint, hold time constraints are typically enforced after synthesizing a clock network. They are very difficult for. Sometimes they are opposite to the setup time or setup time constraints. So it is very necessary to take care of hold time constraints. See, this is what happening. This is the clock. and this is the clock. These are two ing. Why I'm saying the ing here? They're having some kind of skew in between them. Clock skews in between them. This is the clock. It having a skew. It having a skew. It having a positive skew. It having a negative skew. Yeah, it is a kind of skew are there. One, I mean, a positive skew are there, both of them. The problem of short data paths in the presence of clock skew is very similar to whole time violations uh, in flip flop. The problem arises when the data propagation delay between two adjacent flip flop, data propagation between two flip flop is less than the clock skew. See, two clocks are here. This is the second clock, and they have some skew. It has started. It has started. It has started. They have all of them. This is a skew. So the same clock is arrived at the second flip flop later. Then the new data, the second flip flop output switches at the same as the first flip flop, and the same data the first flip flop. This will cause U2 to shift the same data on the same edge as U, resulting in a functional error. See, clocks are coming here. This is a clock. This is a clock. They having a certain kind of skew, and this is the data. But after data, this is there. So what happened? This is the clock. It is again switching here. So what we are happening here? We got it. We should expect this much, but we got this because of that clock. Why? The same clock age arrives at the second flip flop, at the flip flop, later than the new data. New data. It arrives here. The second flip output switches at the same age as the flip flop and with the same data as the first flip flop. This will cause U2 to shift the same data on the same edge, resulting in a functional error. So we will have a data which is not expected. It sees the data differently than this. The same data has been clocked by clocks, same clocks two times because of this length of skew. Length of skew. It is written here. Because of this data, clock Q1 is high here. It sees over here. It will be here. But because this is a whole, this much of timing required for whole set of timing. So this is where it find this. It will go on decreasing, but not there. It's going this way. What we expect, if it is not here, then what we expect here, clock 1 here, it should be go this way up to this, and then there is a change occur. Clock skew and short path analysis. Short path analysis, that means whole time analysis. Clock skew and short path problem emerges when the data propagation path delay between two sequentially adjacent flip flop is less than the clock skew between the two, what we have seen there. See, this is a general delay block in a simple circuits. D1 and clock. This is the TRQ1 required. This is the T clock 1, and this is clock 1. This is required timing for to propagate. The delays are as follows: TQ1, the clock to out delay of the first flip flop. TRQ the propagation delay from the output of the first flip flop to the input of the secondary. The CK2, the clock arrival time at the second flip flop minus the clock arrival time at the first flip flop. This is the clock, this is data 2Q, this is the clock 2, this is the whole time analysis short part, we will discuss the same. See, case A, no problem. There is no problem, then slack is less than T1 minus H, the whole timing. No problem. Problem in slack when T1 minus 1 is greater than, slack is greater than, then case C you find problem T1 minus H is greater less than Sk. This is Sk. Sk is less than T1 minus H. The short path problem will definitely emerge in the circuit if T clock 2 is greater than T clock 1 T RDQN1, that is and minus T whole. If it is greater than this, that is slack is greater than this, then this kind of problem arises, which will arise in B and C. Minimizing clock skew. Reducing the clock skew to the minimum is the best approach to reduce the risk of short path problem. What we simply do there, we just go for reducing the clock skew. Maintaining the clock skew to value less than the smallest flip-flop delay in the design will improve the robustness of the design against any short path problem. Adding delay in data path. First, how we do that? We will add the delay by increasing the routing delay in the data path. This is the data path from Q to D, propagation delay, that eventually increase the total delay of the data path to a greater than the clock skew. Will eliminate the short path problem. The amount of the inserted delay, the data path should be large enough so the data path delay becomes sufficiently greater than its clock skew. That means condition will be happen that slack will be less than T 1, that is this clock time, this much and minus H greater than this. So we have this is less than, this is greater than to this much, so this is less than this. Clock reversing. This is one second way. The clock reversing is another approach to get around the problem of short data path and clock skew. In this technique, clock is applied in the reverse direction. Clock is applied in the reverse direction with respect to data, so that the clock skew is automatically implemented. The receiving flop will clock in the transmitting source value before the transmitting register receives its clock age. This is what happened. It is getting a clock. It is providing a data over here. This clock should reach here before the arrival of this clock. The receiving flop will clock in the transmitting source value before the transmitting register receives its clock age. Alternate phase clocking. To avoid clock skew issues, alternate phase clocking on alternate edges. This method provides a short path clock skew margin of about 1/2 clock cycle for clock skew. What we are trying to do, if this is, they have a clocking on alternate edges, that is edges are 1 2 3 4, then what we do there 1 3 5 4 7 6 or something 1 2 3 4, let's say alternate edge clocking. Between each two adjacent flops there is a safety margin clocking on alternate phases equal to the phase difference of two phases. The usage of alternate phase clocking may require completely different clock constraint on the original clock signals. In the case of clocking on alternate edge, the new constraint on the clock frequency will be half the original frequency. That means if the original frequency f, then the in this case alternating phase, this will become f2, new constraint. Since the adjacent flops are clocked on opposite edges of the same clock cycle, they were here you find they were on 1 2 3 4. Here they will be opposite to that. 1 2 3 4 they will be opposite here. Phase 1 and phase 2. Phase 1, phase 2. It will be on this, it will be on this. So they have alternate phase clocking. Ripple clocking structure. In a ripple structure, each flop output drives the next flop clock port just like the way ripple counter is implemented. The way we use ripple counter there, they will be next flop in the same. Here the sync flop will not clock unless the source flop toggled. This is the sync flop. It won't for this source flop unless the source flop not, it will start toggling. Then it will be get its clock. The output of each counter flop drives the this output and the next flop instead of its data input port. This is we have the flop. So this will limit the clock skew since the flop do not toggle and on the same clock. The first flop is clocked on the positive edge of the clock signal, and the second, third flops are clocked on the positive edge of the output of the previous flop. Previous flop Q. Okay, it's no good. I think it's informative to you. If you have any query and kind of problem, you can reach to me. Thank you. Have a nice enjoying it.